Now, begin at the beginning. Over here. No, first page. There we go. All right, let's get started. All right, so welcome everyone. This is going to be our Introduction to Neural Network Programming workshop. We're going to be doing some neural network programming and workshopping. If you're interested in getting SciNet credit for this, we have an attendance sheet, so please sign it. So if not for your own credit, then for our own records, so we know how many people have been here, and so we can keep track of how much we're teaching, and we get credit from the federal government for it. So it's wonderful that you say you were here. All right. For those of you that don't know me, my name's Eric Spence. I'm an analyst here at SciNet, one of several who do teaching here. I'll be leading the workshop today. If you have questions, please ask. We've also got Marcelo and Ramses in the back who can help us out if need be. Slides are on the education website where they usually are. Hopefully all of you are familiar with the SciNet's education website. Click on the class, and then under file storage you'll see the PDF for the slides. The code is also there. Code and data is in a tarball if you prefer to just grab it from the website. Otherwise you can clone the repository from here. So you'll have the code that you need for the class, for the examples that we've done, and the data we'll be playing with. Data's not huge, but it's about 20 meg or so, so it may take a moment to download. Shouldn't be too bad though. So, okay, why are you here? We're here to learn about neural networks. Okay, the material is decidedly introductory. I aim this really low, mostly because I'm not really an expert in this. I'll just come out right now and say it. Those of you that are actually using neural networks in your research probably have seen much of what we're going to cover today. You may learn a thing or two, but it's likely you've seen much of what we're going to present. Nonetheless, probably you'll get something out of it. We'll be using Python 2.7, whatever your favorite Python 2.7 is. Python 3 will probably work. If you're using Python 3, you probably already know the difficulties that are associated between converting between the two, so you should probably be okay. The Keras framework works on Python 2 and 3, and so that will be fine, though some of the code that I gave you may not work. I didn't test it on Python 3. We will be using the Keras framework on top of, I'm saying a Theano backend, but you can use them if you want to. Both should give you the same or relatively the same answers. It doesn't really matter which backend you use. If you're comfortable with TensorFlow and are already using it, by all means, go ahead. If you haven't, then install Theano instead. But we'll get there. You'll also need the usual packages: NumPy, Matplotlib, scikit-learn, and obviously Theano and Keras. Keras is just a wrapper, so it's small. Theano, not so much. Questions yet? Please ask questions, all right? I know there's going to be a wide variety of people. Who's used neural networks before? Let's just start with that. 2. Awesome. All right. We're in good shape then. You're all on my level. Ask questions, all right? I've never presented this material before. This is all fresh. So if something's not clear, let me know. You probably aren't the only one. Okay? Yes, sir. TensorFlow sucks. That's why. TensorFlow was really, really hard to install on GPC. That's why. Mostly because when TensorFlow was released into the wild, it was decidedly not ready to be released into the wild, and so it was not ready to be installed, and immediately people started asking for it, and so I took like 3 weeks of my life installing it on GPC. We'll talk about these issues later on this afternoon. Okay, so rough, what I'm planning for today is we'll run for about an hour, we'll take a break, 10-minute break, stretch your legs, get a drink, run for another hour, then we'll break for lunch, take about an hour for lunch, then we'll come back and do another 2 hours-ish in the afternoon. I'm not sure we'll have 4 hours of material, probably more like 3.5, but it depends on how things go. And like I said, I've never timed this before, so that's sort of the roadmap for what I'm envisioning for this morning and this afternoon. Okay, so neural networks, you've heard of them. What are they? Why do we care? Okay, so I just went to Wikipedia just to make it easy, all right? Neural networks, also called artificial neural networks, you'll see that term around a lot, are a computational model used in machine learning based on a collection of connected, simple units called artificial neurons. Such systems can be trained from examples rather than explicitly programmed and excel in areas where solutions or feature detection is difficult to express in a traditional computer program. The things you want to take away from this is mostly the end. They can be trained from examples and excel in areas where solutions or feature detection is difficult to express. You don't know how to get the computer to recognize this feature, but you can see it just by looking at it. Neural networks are what you want. Okay? And we'll go over lots of examples of that today, several. Okay? I can see it. My brain can process that. I can totally read those letters. The computer, how do you teach a computer to do that? Neural networks. Okay? If you're doing any pattern recognition of any kind, neural networks are where you're going to probably want to start. There are other techniques out there you can compare against neural networks. In particular, support vector machines are competitive in some contexts. But we're not going to be discussing the relative merits. You're here to learn about neural networks. Where are they used? They're used everywhere now. Image recognition, object detection is a big field right now, especially with self-driving cars. It'd be nice to see what you're going to hit. Natural language processing, when you call the automated phone line and you get to tell Siri what it is you want to do. Neural networks, novelty detection, meaning the detection of outliers in data. Google's next word predictions, when you're typing stuff in and it tells you what you're thinking before you finish typing it. Self-driving cars, again. Medical diagnosis is a more recent incarnation, excuse me. They're showing up everywhere, okay? Anywhere where some sort of pattern is being recognized and the computer needs to identify it and make a decision from it, or just identify it. The classic problem in neural networks originally, this is old now, the old classic problem was this: handwritten digit recognition. How do you program a computer to read those numbers? You can read them, right? No problem. 928-125, got it. How would you go about writing a program to tell you what digits are displayed? The post office never has people reading addresses anymore, right? This has been a solved problem for 10 years, 15 years now. Post office scans it, the computer reads the numbers and decides where it goes, even if it's handwritten. Okay? Well, what would you do, right? You guys are all programmers. How would you start to solve this problem? I don't know. I mean, you can start to see or maybe those are both 2s. How are you going to convince the computer that they're both 2s, right? I don't know. This one's definitely 2. That one's probably a 2. But all you're going to end up with is this huge list of if statements, right? This, that, the other thing, if this, try that. Where do you even start, right? But we have no problems reading that, right? Okay, this is the classic sort of problem. I can recognize this. How do I teach the computer to recognize this? Okay? As Wikipedia said, the neural networks are based on this sort of biologically inspired approach to solving classification problems, and this is one of the problems. Today's class is going to be not focusing totally, but the goal is for you guys to be able to deal with this data set and classify handwritten digits. Okay? So we'll be doing image recognition. That will be the main goal of today's class. Rather than focus on what the individual numbers look like, we're going to take a totally different approach. And this is the approach that neural networks take, which was described in the Wikipedia quote, right? We're going to ignore the details. We're going to break up our data set into 2 or 3 groups. Why? Because this is machine learning. Who's done machine learning before? Yes, of course you have, many of you. Training your model is done separately from testing your model. You do not test your model on the training data. Naughty, naughty. Don't do that, right? You always test against out-of-sample data. So you're going to break up your data into at least 2 sets, the training data set and the testing data set. Optionally also a validation data set, which is used to tweak the parameters as you're developing your model. Okay? And as with other supervised machine learning algorithms, which is generally how neural networks are used, though not always, but generally it's a supervised machine learning situation. We feed the training data into the neural network and train it to recognize the numbers. Okay? Rather than focusing on the details, we're going to ignore the details. The neural network will worry about the details. We're not going to worry about it. Okay? That's the goal of today. All right? By the end of the class, you should be getting over 98% classification accuracy on the MNIST data set, the data set of handwritten digits. Okay? No problem. Easily over 98%. In fact, the best algorithms get over 99.6% right, and the remaining 30 digits or whatever they are, you can't even tell what the person wrote, and so you don't blame the algorithm for not getting it right, because they miswrote the number anyway. Questions so far? Okay, so that's the goal. We're going to back up like 5 steps and start with the basics, which means not doing that just yet. We're going to come to that. Neural networks are built on a concept called a neuron. All that means is a function that takes multiple inputs and has a single output. That's it. Okay? They use this fancy term neuron, which kind of freaked me out when I started reading about it until I realized that that's all it was. It's just a function. All right? It implements, the function that's implemented is up to the programmer, but it must contain free parameters. Why? Because we're training it to fit to data. Generally speaking, it takes this form. So if we have 3 inputs, x, 1, 2, and 3, you're going to multiply 3 weights, w1, w2, w3 against x1, x2, x3, and add a bias, an offset. In vector form, it looks like this, w dot x plus b. Okay? You've got 3 inputs, which means you have 4 free parameters. Did Alex turn the temperature down? He did. Okay. The w's are called the weights, and b is called the bias. Sometimes, in some publications, you'll find that there is no bias because they ignored it, or they don't write it out explicitly and they include it in the weights. Doesn't really matter. The weights are the most important thing. The bias is good to have. Be aware that it could be out there, or it shows up as just a 1 here instead of an x, and so it's the same thing. Just a constant offset to your fit. Okay? That's our function. Everyone with me so far? Questions? Okay. So far. Okay, so we've got a function with weights that we're going to fit. How are we going to do that? Machine learning techniques often take this sort of form. You've got some data features, they're called, and then something you're trying to categorize, say. So in this case, we've got, is it cloudy? Is it hot? Is it windy? If so, do I go to the beach or not? Yes or no? How windy is it? How cloudy is it? How hot is it? Okay, so your function might look like something like this, okay? Some weight 1 times whatever the cloudy number is, times weight 2 times how hot it is, weight 3 times how windy it is, plus my offset. If that's greater than 0, then I'm going to go to the beach. And if it's less than 0, I'm not going to go to the beach. Okay? Simple classification problem. I need to find W1, W2, W3, and B such that this function works to some accuracy, as accurate as I can get, right? So the question is, how do we optimize this, W1, 2, and 3, and B, to match our data? This is called supervised learning, meaning I know whether I went to the beach or not, given the data. I have something against which to train. We're going to be using minimization of a cost function is what it's called. Okay, we're going to create a cost function, some sort of measure of how wrong are we. In this case, I'm going to take my function, input the data, subtract the answer, which is v, and then square it, and then add it all up. This is your quadratic cost function, it's called. Not surprisingly, you've seen this before in other contexts, right? Least squares is based on the same concept. Okay? The object of our analysis in this particular case is to minimize this cost function such that it gets the most possible points right out of the data set. A perfect minimization would be a cost function of 0. Usually you don't get it that good. Sometimes there are data you can't fit. But as a general rule, that's what we're after. This sort of approach shows up in all sorts of other contexts, right? Any sort of fitting algorithm is going to be doing this, right? Least squares, for example, does the exact same thing, right? So we need an optimization algorithm that will find the minimum of C. Good? Who's with me so far? Everyone's okay? Okay, this is not very advanced. In fact, the example we're going to be doing is actually trivial, but I want to do it anyway so you can go through the motions and see what we're doing. Now you'll notice a problem. What's the problem with what we've done here so far? Has anyone seen it? Here, I'll give you a hint. We'll go back to the last slide. Do you see the problem with what I've just proposed? We have a binary target. My function has only 2 values. Not very useful because I like to use calculus. And calculus does not like functions that do that. Right? Well, I mean, it depends what field you're in. But those of us that are physicists by training like well-behaved functions, as we call them. Not well-behaved. So we're going to use a different function. We're not going to use that function. Instead, we're going to use the logistic function. Though in the literature of neural networks, you'll find it called the sigmoid function more commonly. So we're going to call it the sigmoid function. This function here, 1 over e, or 1 over 1 plus e to the negative z, where z is our argument. So if we stick in our previous functional form, it's going to take this form, 1 over 1 plus e to the negative w dot x plus b. Okay, sigmoid function. Remember that name. Okay, why do we use the sigmoid function? Because it looks like this. You've seen it before if you've done any sort of logistic regression. Lots of classification algorithms are based on this, right? It transitions nicely from 0 to 1 continuously. And I can do calculus on this, right? Obviously, this is much easier to work with. Okay, so let's not use our original function. Let's use the sigmoid function instead. Okay, because I have the sigmoid function, now I can approximate the changes in my cost function like this, right? Change in my cost function is partial of c with respect to my weight times delta w, partial of c with respect to my bias, delta b. Okay, changes in the cost functions can be approximated as linear changes to the weights and biases. Okay, so now I can start using minimization algorithms to minimize my cost. Who's used minimization algorithms before? There are bazillions of them out there. Choose your favorite, right? Gradient descent, simplex, simulated annealing, Monte Carlo methods, they're all tons and tons and tons of them, okay? We're not going to be using tons and tons of them. We're going to be using one in particular. Who hasn't gotten the data yet? Get the data, okay? If we haven't done it already, git clone that address or go to the website and grab the tarball. Okay, this slide has nothing on it. All it is firing things up. But sometimes people get stuck at the firing up stage. So I wanted to put it out here. Okay, clone it. What's that? Go to the education website. It's there too. Okay, I'm going to be running everything in IPython because IPython is better than Python. The end. With PyLab invoked. Okay, if you don't know what this means, don't sweat it. If you're happier in Python, straight up Python, that's fine. Straight up Python works. I've tested the code in straight up Python. If you use PyLab, things are a little smoother, but you're not obliged to. Everything will still work. Some people, in my experience, especially at workshops, and I don't blame them, like to cut and paste code from PDFs into Python. This will fail because I use underscores in my variables, and underscores do not cut and paste well out of PDFs into code. So if you're cutting and pasting out of code, which is fine, be careful before you raise your hand. Make sure that the underscores are intact when things fail. Does that make sense? Right? There's going to be a lot of, if you want to, there's a lot of typing today. Cutting and pasting is not a bad idea. Or copy and pasting. You can't cut. Copy and pasting. I use underscores in my variables quite a bit, and consequently, copying and pasting may be problematic. So your code, oh, that's not the right one. Let's pull up my window. So here I am. I'm in the code directory. Everything I'm going to be doing is run from the code directory for today's class. You'll notice there should be 4 files in there. We'll have two networks, first network, second network, some plotting routines, and then the code that loads the handwritten digit data is what you should find in there. Okay? So if you see, when you read my syntax, it's assuming I'm in that directory. That's why I'm telling you all this. So that if things if you can't find the code, it's because you're in the wrong directory. Okay, let's do an example. Okay, we're going to go straight to data with a single neuron, and we're going to minimize it so that we can find a classification situation. All right, so let's go through this data. Actually, let's go through. You guys can start typing. I'll explain what you see here. So, scikit-learn, model selection and data sets. We want to import both of them. As you'll notice throughout the class, I like to keep my namespaces intact, so I always import something as something. Okay. We'll import plotting routines. That's my code there that I wrote as PR. Then we're going to invoke the make blobs routine. This is from scikit datasets. Okay, just make some blobs of data.
Right.
Yes, sir.
Comment on the last. You said that you like to keep your namespace as an important thing.
Right. You could do from scikit-learn sklearn datasets import make blobs. But then, in the case of make blobs, it doesn't really matter because there are no functions out there called make blobs, except in this one, presumably. Maybe there is, I don't know. But if you have a function that has a very common name, then you're going to have conflicts, right? For example, we'll be using round in this class. The default round function is different from the numpy round function. They're different functions because the numpy round function will round an entire vector while the default round function will not. So this prevents conflicts between function names. That's all it's for. All right, so we're going to make blobs. We're going to make 500 data points, centers, two centers, and a center box of negative 3, 3. Don't worry about what these things mean. Okay, you'll see the data in a second. I'm then going to split my data into testing and training. Okay, 2 sets. So I'm going to use this sklearn model selection, train, test, split. I'm going to split the positions and the values. So what's happening with make blobs is that it's going to create data points, 500 of them, on the xy plane, so 2 coordinates, and they're each going to be given a 0 or a 1 value. And the goal of what we're doing is we want to classify our 0s and 1s. Which one's which? We're going to split the data set, the positions and values. This function will split it cleanly, so I'm going to split into training positions, testing positions, training values, and testing values. Use whatever variable names you like. I like things to be clear, but you can shorten it up if you like. If you want to see what it looks like, the training positions, there are 400, each with 2 coordinates. That's your x and y positions. The values, there are only 400 of them, 400 0s and 1s, depending on which category it got put in. And then here's some example of the training position data. So you got your 2 dimensions, and the training value is 1 for that particular example. If you run PR plot dots with those, you can see what this looks like. Let me do this quickly so I'm on the same page as all of you here. So, see if I can pull this off. All right, import sklearn model selection, import sklearn datasets, good. Import plot routines, SPR. Did that plotting routine work for everybody? Yes, good. No, maybe. Make blobs 500, centers equals 2, center box equals -3, 3. I've done this before. PR plot dots. No. Dots, dots. Okay, should look something like this. Your plot will look different. It's based on random numbers. Okay, so your centers will be in a different spot than my centers. Your blobs may be in different spots. Semi-distinct blobs of data points of different colors. One color, the oranges are the 0s, and the blues are the 1s. Good? Or how about bad? No one wants to admit it. Okay, that's fine. Okay, so you've got your data. This is our toy data. We're going to now build a network that will classify these. So what's the goal? Given a 2D position, so we have 2 inputs, x1 and x2, we want a network which can correctly classify the data point as 0 or 1. To keep things simple, very simple, we're going to use 1 neuron. Grand total of 1. We'll use the sigmoid function, which we just talked about, okay, with the 2 values of the position as the inputs, and we're going to use the technique called gradient descent to minimize our cost function. Who's used gradient descent before? Some of you have. Okay, it's a fairly common technique for minimizing cost functions. Okay, the goal is to find W1, W2, and B. There are only 2 weights because there are only 2 inputs, right? Get out of there. What's that doing here? Get off my slide. There we go. Here's our sigmoid function again, in case you forgot what it looks like. Here it is. Again, we only have 2 inputs, x1 and x2, so we have 2 weights plus our bias. Good? Bad. Nothing. Okay. All right. Gradient descent. For those of you that aren't familiar, gradient descent is one of many algorithms out there that are used to minimize cost functions, or any function for that matter. Okay? The goal is to minimize No, I already said all this. We're going to minimize this thing. Here's our cost function. There's the original way I wrote it out. Now I've written it out with our x1 and x2, w1, w2, and b. Vi are the values, ones and zeros, right? We're going to use the quadratic cost function like we talked about before. So we're just going to square everything. I wrote that. So you have to be in the code directory to. Okay, so the idea behind gradient descent is to calculate the gradient of the cost function and then move downhill by going down the negative gradient. Okay, if you've never seen it before, this is sort of the textbook picture of how gradient descent works. You've got some cost function. In this particular case, we're just going to call it x squared. We want to minimize the function. We're at some value of x. We calculate the gradient. We take the negative value of it, and then we step by some amount. The amount we step is determined by this parameter called eta, which is called the step size, I think. Step size, yeah, there it is. Okay, eta. So we iterate on our function, and we march in our parameter space until we minimize the value of the cost function. If we have multiple parameters, as we do in this particular case, w1, w2, and b, in that case, we're going to iterate all three parameters at the same time to find the minimum of our multidimensional space, to minimize the cost function. Okay? Good? Okay. At least two people nodded. I'll take that as a majority. Yes, sir.
What exactly more or less is defined?
Okay. The goal is to classify these into ones and zeros, right? These are the zeros. Position. All right, so we've got two positions, so they're more or less separated by position, right? x1, x2. So given x1 and x2, we need to find w1, w2, and b that minimizes the cost function. And the cost function has the value in it, right? That v, the ones and zeros here. So we're going to grind through, change these parameter values to minimize c. And that, by minimizing the cost function, indicates that we've done the best we can to categorize them one way or another. All right? Other questions? Okay. So we need to find the derivatives of our cost function with respect to w1, with respect to w2, and with respect to b. There's f. I'm going to call this function f. Here's the cost function. F at I minus v at I squared, 1/2 sum over. If you take the derivative of that function, you'll have to take my word for it, or work it out yourself if you prefer. This is the answer. Derivative of c with respect to w1, derivative of c with respect to w2, derivative of c with respect to b. They're essentially the same, except this one has an x1 on the end, this one's got an x2 at the end, this one has nothing. But you're over them, so it's not quite the same as just tacking on an x1, right? These are vector quantities. So you have to do the multiplication, then sum. Good? Questions? Okay, and so to update our parameters, we have the derivatives, we just saw them. Update our parameters. W1 goes to W1 minus eta times partial of c with respect to W1, which we saw in the last slide. W2 goes to W2 minus eta times that quantity. B goes to B minus eta times this quantity, where we remember that f is this. Did you see it? Did you miss it? You want to go back again? Go back again. These are the derivatives. Partial of C with respect to W1, partial of C with respect to B. You can work it out by hand if you want, or you can take my word for it. And that's how we update the parameters using gradient descent now. Okay? Okay, let's do it. I've written the code for you, so you don't have to write it. It's in that file, firstnetwork.py. Let's go over the code quickly because it's not very complex. I define a couple of functions. The first one I'm going to define is called the sigma function. It does exactly what you think. It's the sigmoid function. Okay, I give it x and I give it my model. The model is just going to be a dictionary that contains all my parameters. In this case, the model just contains W1, W2, and B. There they are. So I create this variable called Z, which is just model 1 times x1, model or W2 times x2 and B. And then I return the sigmoid function, right? 1 over 1 plus e to the negative z. Okay. And then all I need is this function called build model. Build model is going to take my model, take my data, and do the gradient descent. So I initialize my model randomly, just some random numbers. Doesn't matter where we start. That's not true in general. For this case, it doesn't really matter. Okay. Some parameters that we use later on. I run my forward problem. So I'm going to take my data, run it through the sigmoid function to get my value of f. Okay. Now I'm going to iterate. However many times, 10,000 times. I'm going to calculate dc dw1, partial of c with respect to w2, partial of c with respect to b. Those three quantities we saw on the other slide. Then I'm going to update my parameters. W1 becomes W1 minus eta times d, partial of c with respect to W1, so on and so forth. And then I'm going to run the forward model again, and then I'm going to check to see if this is my best fit yet. There's a bunch of other stuff in the code. You can read it, and I print out some stuff if you want to, and then we return the best model. Questions about the code? You can look at it. It's there if you downloaded it. But the important pieces are here. Good? Okay. Let's run it then. Import first network as fn. Model equals fn. Build model. Give it the data. Give it the values. I picked this value of eta. It seems to work pretty well. 5 to the times e to the minus 5, so a small value. And then run it. Doesn't take long. The data set's small. Do it. Get off my screen. There we go. Where are we? Okay, so import first network as fn. Model equals fn build model. .8, not great, but that's okay. Once you're done, once you've got your model, you can plot what's called the decision boundary, which says where does my model think, how does my model split one data point from another? Sorry, wrong one. fn. Where's my plot? There it is. Ugh, hold on. Yours will look different, right? Your data was randomly different than my data, but you'll get something that kind of sort of looks like this. We're going to have a red area, we're going to have a blue area. That's where the model decided the boundary was between the two data sets. That's why I only got 82, 83% right. And you can see why, right? There's such a huge overlap that my model is not going to be able to do much better. But that's okay. The point is just to illustrate that we're going to use gradient descent to minimize our cost function, to update our parameters, and get the best model we can, given the data. That's the only point of this exercise. Did everyone get something that looks like this? Who's got problems? I mean about this, not in general. We don't have time. I have problems. Okay, so we minimized our cost functions, and we got a fit. It can classify our data as best it can. So now what do we do? Well, we have to, so there's the data from the slides. Similar idea, two blobs, kind of sort of separated, a big mess down the middle, and the minimization finds the best fit it can. Okay? But we have to test against our test data. Of course, after you train your model, you must test against the test data, because that's what actually counts, not training against the training data, especially when you get 100% right. Test against the test data. So we run the test on, on the test data. So I'm going to import NumPy explicitly, though I don't really need to because oh brother, come on, import NumPy as NP. We're going to run fn predict. Predict is just going to run the forward problem. If you haven't looked at the code, it's in there. It doesn't do anything special. Okay, and then I'm going to sum up the correct answers and then normalize it so I can see how we did. And I got 88% on the test data. Again, your answer will be different depending on where your blobs were. I've had sometimes when I've run this example, I've had blobs that were totally separated and I got 100%. It was awesome. But that's not usually how it works. So always test against your test data after you're done, right? Because that's the actual fit that matters. Whenever you do machine learning of any kind, whenever you're fitting a model, you test against the data you held back. Good so far?
Question.
Yes.
I was kind of surprised at first, but maybe it's actually obvious, that the decision boundary is actually linear. Just because I thought the sigmoid would change something. It's like
we're about to talk about that. Let's talk about that. Okay, the reason it's linear is because I've got three pieces of data, or two input parameter, 2 dimensions, and 3 parameters. So it's going to be linear, right?
even with sigmoid, like
The sigmoid is just how we're processing the data as it comes in. But when we plot, the decision boundary itself will be linear because you only have 3 parameters. Yes, sigmoid, it doesn't matter what function you would use. Okay, so let's talk a little bit about our first example. Okay, actually you got my first bullet for me. All right, it's linear. Okay, it's going to be linear. Only 3 free parameters for 2 independent variables, right? So we can only do a linear fit. Okay, the fit worked as well as it did, more or less, because, well, I separated the blobs explicitly, right? We'll do better. 88% is really not that much. Don't publish 88%, okay? It's not very good. We'll do better with some examples we'll be doing later. Your result will be different. If we want to categorize more complex data, we're going to need a more complex approach, as you might imagine, right? Obviously, linear fits, if we could do handwritten digit recognition with linear fits, we'd do that, but we can't, right? Otherwise, well, we wouldn't have this class. Questions? I had another point. It's already gone. How are we doing on time? 10:02. Oh, I'm going fast. All right, let's start this a little bit and then we'll break. Okay. So that's one neuron. It's impressive, isn't it? This is where we're going. Suppose instead of one neuron, we did something a little more involved. Suppose we bundled a whole bunch of neurons together in layers. The first layer is called the input layer. It has no function. These are called neurons, but they're really not in the sense we've been thinking. They just feed the input data into the network. Okay? That's all these are. That's why they're smaller. Okay? Just feeds the input. Then we have as many layers as we want. These are called hidden layers. And then we have the final layer. It's called the output layer. The hidden layers are neurons, as we've discussed so far. Each of these has a function in it. Let's just say it's the sigmoid function for sake of argument. Each of them has a sigmoid function in them. Each of them has its weights and biases. Okay, so this one is going to have 4 input values, 1 for each neuron. So this will have 4 weights and a bias. So 5 free parameters. This one will have 5 free parameters. That one has 5 free parameters. We're up to 15. Each of them only outputs one output, as we discussed. The function takes as many inputs as it needs to, outputs one value, like all functions do. So these arrows should be interpreted as all the same value. The only reason I wrote them all out is because they go to each of the next layer. Next layer's neurons. So this neuron has 3 weights, 1 for each neuron that fed it, plus a bias. This one has 3 plus a bias. That one, all of these. The number of weights and biases for the hidden layers depends on the number of outputs that fed it from the previous layer. Finally, same thing with the output layer. The output layer takes the inputs from the previous hidden layer, runs its sigmoid function with its weights and biases, and then outputs. Good? Crazy? Oh man, you're absolutely right. Okay, let's do that one more time. The input neurons do not contain any functions, right? They're just feeding the network. They're there mostly for graphical purposes, to let you know this is where the data is coming from. Comes from the input neurons. Then we have the hidden layers and the output layer, they all contain functions. In our case so far, sigmoid, but we'll look at other functions later. Okay? Each neuron outputs just one value. Okay, despite what you might think from the graph, that's why this might be slightly misleading. These are all the same, these are all the same, right? Same with these 3 values are all the same, right? This input neuron is feeding the same value to all those blue neurons, okay? The number of free parameters in any given layer depends on the number of nodes in the previous layer, right? The output from the output layer is then aggregated into the desired form before it's fed to the cost function. First time I saw that, I was like, oh yeah? Seriously? Seriously? Yes, seriously. This simple biological networks may have this form, very simple, very, very simple, okay? Takes the input from the previous layer as its output, or as its input, and processes it, and feeds that information to the next layer, which feeds it to the next layer, which feeds it to the next layer. The idea here is that each layer is making decisions about the information that it received from the previous layer, processing it, and then feeding it to the next one, which takes that information, makes decisions about what's in there, processes it, and then feeds it to the next layer. Each layer can make more and more complex decisions this way. Or so goes the hand waving. And I kind of mean that seriously. At some level, we don't totally understand how these things work. At some level. At some level, we do. A lot of good theoretical research has been building up in the last couple of decades on these things. But they're very complex, highly nonlinear, as you can see. Which means that there's a lot of, this is ripe work if you want to do some theoretical neural network mathematics. There will be a job for you. Potentially we can do some very sophisticated decisions with this sort of network. Okay, this is where we're going. There are subtleties in training the network. This is my understatement of the day. There are subtleties, because that was the first thing that hit my mind, right? Okay, I know how to train one neuron. In fact, we didn't even have to train the first neuron if you think about it, right? I could have just done least squares on that thing and gotten an exact answer, right? We didn't have to use gradient descent. But how on earth do I get D, C, D, W from this guy when C is way out over here? Oh, good Lord. That's what hit me first. And the amusing thing is that it's actually a solved problem. There are algorithms for finding the gradient dw, di, or dwi and dc, oh my goodness. Partial of c with respect to w sub I, partial of c with respect to b for every neuron in there. Okay? That was the scariest part, because you got to find that for all the neurons, right? Otherwise I can't run gradient descent. I can't update my parameters without partial of c with respect to everything. But how do you get it? Well, and there are lots of them, right? If you started counting how many parameters there were in here, where are we? 15, over 50, right? For this one, and this is small. We're barely getting started. Okay, the answer is it's a solved problem. Okay? Amusingly, this was actually solved in the 60s before anyone realized what they were doing. The next two slides are completely ignorable, okay, if you so desire. The answer is what's called the backpropagation algorithm. And once you see how it works, you'll understand why it's called that. How do I get the partial of c with respect to some weight somewhere buried inside my network? Okay, let's do some terminology first. The input layer is going to be called the 0th layer. Okay, X takes the form of R 500 by 2. We're going to use the previous examples data. Okay, our 2D space, 500 data points with 2 coordinates, X and Y, or X1, X2. So it's 500 by 2. That's our input data. Okay. A1 is the output vector from the first layer. So I calculate what's called Z1, which is I take the transpose of the data. This is my vector array of weights, right? All the weights for one neuron by all the neurons in that layer, plus all the biases for that layer. That's Z1. I run it through my sigmoid function. Okay, that's the output of the first layer, A1. Okay, W1, as I said, is K 2 by K. Okay, K is the number of neurons in that hidden layer, the first layer, the hidden layer. Okay, it's arbitrary. We can make it, the only things that are fixed are the inputs and the outputs, right? The output has to have a certain form because it's supervised learning, right? You know the output is either, in this case, 0 or 1 for this particular example, the first example we did. The outputs are either 0 or 1, and the input has to be 2D, right? x1 and x2. That's the only constraints we have. The number of hidden layers and the size of those hidden layers is completely arbitrary. Here's k. That's going to represent our first hidden layer. Is going to be k by 2. B is k by 1. Okay? For an arbitrary layer, hidden layer inside, including the output layer, the nth layer has some weighting matrix. A is the output of the previous layer plus the biases for that layer. You'll notice the symmetry here, okay? The only difference is that the first layer takes the data itself as its input. All the other layers take the output of the previous layer as their input. Then we get the output of that layer. And those are all the dimensions if you care to see them. We haven't done anything yet. Just defining some things. Like I said, this is all completely ignorable. You can read the details later if it interests you. I want to go over it for those that are interested, and for the sake of seeing the code later that actually uses it. Okay, here we go. This is the backpropagation algorithm. I start at the end, so I run my whole data forward through my network. I'm at the end, so I've got my cost function now. Okay, I want to get the cost function, the derivative with respect to z of m. M is the last layer. M is the output layer. I'm going to define this function, this quantity called delta m. That's what we're going to call the error of the mth layer. Mth layer's error is partial of c with respect to z of m, which is the gradient with respect to a of m dotted with sigma prime when we're using the sigmoid function. Take my word for it, okay? Remember that our cost function looks like this. Notice that we're using a now as our as the output of the network instead of f. Chris?
Vector product or a Hadamard product?
That's a Hadamard product, which just means element by element. Because of that, you can calculate this. Okay, that's just that up there. Okay, our error in the mth layer, the error in the output. I now claim that the error in the nth layer is this quantity. Sigma prime, which is the derivative of sigma with respect to z of that layer. The weighting, the matrix of weights of the next layer transposed times the error of the layer ahead. This is why it's called backpropagation. I start at the end, and then I can use the layer ahead of me to get the error in the layer I'm in. So I start at the end, then I get the error in that layer, and then I get the error in that layer, and then I get the error in that layer, and then the answer is that, as it turns out. You can do the math yourself. The partial of c with respect to b of the nth layer is just delta of L. The partial of c with respect to the weights of the nth layer is a of the previous layer, the layer behind delta L. Whew. There was a hand up. Chris, yes?
L indexes from 1 to n, and I indexes from 1 to, I guess, n. Clear, arbitrary.
I are the data points. L indexes from 1 to m.
Yeah.
Arbitrary number of layers. No problem. Questions? Yeah, I didn't expect any. That's okay. The algebra is not that hard, but we're not going to do it here because it's beside the point. The point is that you've seen it now. This is how the algorithm works. You go run the data all the way through the network as it currently exists. Start calculating these quantities that will give you the derivatives you need to update your parameters using gradient descent. Because now we have those derivatives we were after, right? What's the time? It's 11:05. What's next? Okay, we're not going to do the next example. Let's take a break. Take a break. What time is it? 10 minutes. Let's meet at 15:15. All right, guys. Let's get back to it. All right, so just to review. Let's review here. Once more. We're going to construct a network that kind of sort of looks like this, something of this sort of architecture. Okay? We need to be able to update our parameters because all of those neurons have their free parameters of their own. And we just went through the backpropagation algorithm, which gives us the values of the partial of C with respect to W, partial of C with respect to B for all the layers so that we can do exactly that. Like I said, this slide and the slide previous you don't need to know the details of. Just know that that's the name of the algorithm, so when you're in an interview and someone asks you, you can say, yeah, well, backpropagation algorithm, of course. I'm like, oh, okay, good. Okay, that's all you need to know. No one actually knows how it works. Shh. All right, so let's do another example. So same sort of commands as last time, except instead of using make blobs to generate our fake data, we're going to use make circles now. Again, 500 data points. You need a noise parameter in there. Noise of 0.1 seems to work okay. And then the same thing as before. We're going to split our testing and training data. Split our data into training and testing data. Again, test size of 0.2. And again, run the same function we did before, PR plot dots, so we can see what our data looks like this time. Instead of having two blobs, we're going to have circles, as you might imagine. All right, pause, value, make circles. Okay. Sorry, I forgot my N. Okay. Split that up. Okay, PR plot dots. Oh, where's my, hold on. Oh, that's not right. Let's clear that up. Okay, does everyone have their dots? Got your circles? Yep, nope, take your time. All right. I realize some of these lines are a bit long. I use long variable names so that they're clear. Okay. Now the goal is going to be the same as last time. We're going to have an X position, we're going to have a Y position, or an X1 and an X2 position. We're going to have a 0 and 1 labels for each data point. Sorry, did you? Here, go ahead.
Did you see my face?
Yes. Here, I'll pull. You got it. Here, let me pull up mine. So yours should look something like this. Okay, more like this than last time. Last time the blobs could have shown up anywhere. This time the data shows up more or less the same. We've got a ring of blue dots. We've got a ring of yellow dots. And there's sort of kind of a boundary between them. Obviously, a linear fit's not going to work this time, as you might imagine. Yes?
Okay, why is there a line kind of in between them? That seems sort of arbitrary because it's just a cluster of points and you choose to line like any radius, I guess.
I don't know. That's where make blobs put it. I imagine there may be flags for moving it around. I just grabbed the default. All right, let's move forward here. Okay, so your data looks something like that. Yes? Yes? Something like that. Okay, now, here's our plan. Okay, the goal, as we said, same thing as last time. Okay, we've got two input data points. We've got the x1 and x2, so they're coordinates on the plane, and we've got a classification of 0 and 1. And the goal is create a network that is capable of predicting the value of the data point based on its position in the plane. Okay, we can't use a linear fit, as we said. It's not going to work quite obviously. This time we're going to create an actual neural network. It's going to have 3 layers, just 3. Okay, the input layer, one hidden layer, and then the output layer. We will use the sigmoid function for all of our neurons. That would be the hidden layer and the output layer. Okay, with the 2 values of the position as the inputs to the hidden layer and the outputs of the hidden layer as the inputs to the output layer. The number of neurons in our hidden layer is arbitrary. We can change that around. The code has to be able to handle that. Okay? Again, we're going to use gradient descent to minimize the cost function to find the values of our weights and biases, the W's and B's for our neurons. Good? Same exercise as last time, except this time we've got an actual network. Okay, so this is what our network's going to look like. 2 input neurons, x1 and x2, 2 output neurons, 0 and 1, an arbitrary number of hidden neurons, neurons in the hidden layer. People always ask, and rightly so, why 2 output neurons? Right? I could just use 1 and have the output be 0 or 1 from a single neuron. And the reason, generally speaking, is that this way I can actually do a probability if I want to, right? Probability of a 0 versus a probability of a 1 if the network's not sure. And more generally, this generalizes better to higher output dimensions, right? If I need to, say, have 10 digits I need to classify, just to pick a random example, you need 10 output neurons, right? Unless you want to use base 2, and then you could get away with 4 output neurons, but that just complicates matters. Everyone just uses 10 output neurons for the handwritten digit recognition problem. We're going to use 2 output neurons for this problem. Questions so far?
So when you do the backpropagation.
When you do the backpropagation, you start here, then you work here for the backpropagation. When you're getting the output, it's going to be a 2D output now, right? And so what we will do is we'll take whichever one's biggest, that's what we're going to call the 1. Or whether it's, sorry, whichever one's biggest is going to be the flag to indicate which digit it is. So let's say this one represents 0 and this one represents 1. If this one's the bigger one, then we'll call it 0. If this one's the bigger one, we'll call the output 1. In whatever output the network generates. Maybe? You're not sure. We'll do it one more time. This output will represent 0. This output will represent 1. If this output here comes out bigger, then bigger than this one, we'll call that the correct the decision of the network. We'll call this one's bigger. That will be the decision of the network. In reality, it's never 1 and 0. It's always 0.79 and whatever. But you have to help your network along a little bit. Other questions? Okay. The code. We're going to go over it briefly. This is secondnetwork.py. You downloaded it. The first slide is just helper functions. Okay? Sigmoid function. We've seen it before. There it is. Sigma prime. This is the derivative of sigma with respect to z. If you don't believe me, knock yourself out. Calculate it yourself. Okay. Predict. All predict does is run this code, the forward. Okay. And does exactly what we just said. Okay. It runs the forward problem, gets the A2, the output of the last layer, because there are only 2 active layers, right? The hidden layer and the output layer. So that's A2. And then takes the max arg. Argmax is going to say which of the 2 is bigger. That's my answer. Okay? Axis 0. And if, take my word for it, it's going to do what I say. It's going to do what I say. It's do what I claim. And if not, you can play around with Python and convince yourself that that command does what I just said it does. It's going to give you which index is the bigger one, 0 or 1. It's just an index counter. But because 0 and 1 are what we're after in this case, it works. Okay. The forward function, all it's doing is running the data in the forward direction. Okay, so it takes the data, x, and the model, which is our dictionary of parameters. We calculate Z1, which you remember from our backpropagation slides. Model W1 dotted with the transpose of the data plus the model. Okay, then we take the sigma function of it, and then we repeat Z2. Dotted with the output of the first layer. A2 is sigma of Z2. And then for kicks, I return everything. So it turns out I never actually used Z2, but just ignore that point. Okay. Good so far? We're just marching through the layer, or in the forward direction. Okay, now, building the model. We've got a lot of arguments here. Let's just look at a couple of them. The first one is the number of nodes. The hidden layer, like I said, has an arbitrary number of nodes in it. So that's an argument. X is our input data. V are the values. Eta is our gradient descent step size. The output dimension, I could have hard-coded. I decided not to because we're going to use this same code when we do the hand digit recognition. So I need to be able to change the size of the output. Output dimension is 2 in this case. Number of steps. Okay, so the first thing we do is we build the model. Initialize it randomly. You'll notice that these are not scalars anymore. These are all matrices. Well, B is really just vectors, but you need to add the extra dimension on there because of NumPy issues. I run the forward model. Then I start iterating. These variables correspond to the variables we saw during the backpropagation slides. Okay. Of interest might be to you this particular line here, delta at V, range of length V minus 1. This is subtracting off the data. So everywhere where V is equal to 1, I'm going to subtract 1, is essentially what it's doing. And that's for calculating our cost function, right? The function, or the output of the function minus 1 squared. That's where this is coming from. In theory, you could do the same thing with the zeros, which you should, but I'm just subtracting 0, and that doesn't do anything. And so I didn't put that one in. Okay, that's this line here. The mth A minus B is what that corresponds to, if this line is strange to you. Delta 1 for the first layer is that, and there are your partials. Partial of C with respect to B2, partial of C with respect to B1, W2, and W1. Update our parameters. Lambda is 0 for now. We'll come back to what lambda is later. Okay. These ones are correct. Okay, itself minus, these are the same lines as last time, as the first example. The model, B1 minus itself, or itself minus eta times partial of C with respect to B1, partial of C with respect to B2, and so on. Good so far? Okay, it's not totally obscure.
Well,
Yes?
Specifying the dimensions of the hidden layers, like how many nodes you have in each of the hidden layers.
So that's num nodes.
Oh, sorry, it's the same.
So for this particular code, there's one hidden layer only.
Oh,
Okay, for this one. That's why I've hard-coded B1, B2, W1, W2. Otherwise, there would be W3, W4 for however many layers you have, right? Other questions? Okay. Let's do it then. Import second layer as SN, or second network, excuse me. And then the code is almost the same. You have to specify the output dimension this time as 2. Training position, training value. For this example, let's just use 10 hidden layer nodes. And then eta of 0.01. Oh, get out of here. Excuse me. All right, so what have we got here? Import second layer, second network. There I go again. As SN, model is equal to SN, build model, 10, train position, train value, output dimension, eta, number of steps, and the others are not needed. Let's just fix that. This code's a little old. Seems to have made a decision. Good? Does it work? Maybe? We're not sure. Still thinking. Once you've got your model, plot it, just like last time. Plot, decision boundary, training positions, training value, model. This time it's sn.predict instead of fn.predict. And you'll get something that looks something like this, depending on your data, right? Yes? No. All right, so you can see that the data was a lot more complicated. Obviously, linear wasn't going to do it, but the model with this many nodes was capable of looking around and doing the best that it could, given the mishmash nature of this boundary, to distinguish between one set of points and another. You throw more nodes at it, you'll do better, because there are that many more parameters, right? Always test against your test data. So let's do that quickly. F is equal to sn.predict, test position, model. And then again, we do the sum, test value, float, test length value. And I got 85 on my test data. Again, it's not that surprising that it's not that good, given the nature of our boundary here, right? Things will get cleaner when we start dealing with the handwritten digits, because those are, generally speaking, a lot easier to classify. Everyone with me? Yeah? So far, so good? Okay. Let's take a look. This is 73. I got 85. Again, it depends on the random numbers, right? Everyone's going to get a different number this time. So we built our model. Now we're going to run the test data forward through it, and then we're going to compare it against the test values. This is not the cost function. No, this is the score, the quality of the against the test data. How well did the model do against the test data that it hasn't seen yet, right? That's what we got. Other questions? Yes, Chris.
Can you comment on the choice of the learning rate and how it was kind of e to the -5 before and now 0.01?
The things work out nicely because I spent a few hours grinding through, and it's not so nice. No, one of the things you'll find when you start training your own networks is specifying these parameters takes a bit of trial and error to find values that work. There's a lot of art in this. It's not always clear where to start. There are some guidelines in terms of number of parameters versus number of data points. So it depends on what framework you're using. No one's going to code neural networks like this, the way we've been doing it. The second half of the class will show you how to do it properly. The purpose of going through these steps is so you can actually see what's going on under the hood. So again, when you're at the interview, you can say, understand, yes, I ran into the exploding gradient problem. It was very embarrassing, and so I adjusted my parameters and threw in another layer, and boom, everything worked. And they'll be like, oh, he totally knows what he's talking about. All right. Okay. So trial, you went to the next slide, you cheater. Look at that. Trial and error. Ada is found by trial and error, I'm afraid. Okay. Our model has lots of free parameters, as you might imagine, right? We threw in 10 nodes with 2 inputs, so that's 11 each, 22, 11, 22, plus the output. We're getting a lot of free parameters in there. It does a pretty good fit. This is an important point, and we're going to spend some time talking about this. Okay, it's not uncommon for the number of parameters in the network to greatly exceed the amount of data you have. And if you've done any fitting ever, which you all have, some warning bells should be going off in your head. When the number of free parameters in your model exceeds the amount of data you have, you've got a situation ripe for overfitting, right? I can fit my data really well. But this is a very common problem. It shows up all the time in the very complex neural networks. I'm going to show you how to deal with that right now. But it's something to be very aware of. You have to be careful because these because I can throw a network at you with 100 hidden nodes in the first hidden layer and 100 nodes in the second hidden layer. And if my input data is several hundred data points, suddenly I've got tens of thousands of parameters, right? This is a problem, okay? Ripe for overfitting. This is another reason why we separate out the testing data from the training data. Always, always separate it. You cannot check the quality of your model with the data you trained it on, because you'll do really well, but it's not going to work on any other data, right? Okay, so there are techniques out there for improving the generalization of the model, and we're going to come back to those in a minute. Let's switch gears. We're coming back to the point of this whole class. Handwritten digits. Okay. MNIST is the name of the data set. It's NIST, National Institute of Standards and Technology. They're the ones that gathered the data set. I don't know where the M comes from. This is called the MNIST data set. It contains 60,000 training and 10,000 test handwritten digits written by 500 people. 4 souls got sat down and they wrote out 1s and 2s. And so there are now 60,000 of them. They've been size normalized, centered, and they're all grayscale, 28 by 28 pixels. Okay. We're going to use the same code that we just used to do a first attempt at classifying the MNIST data set. Note, I'm going to note now that when it says 60,000 training, in the code that I've given you, it's actually going to be split into 50,000 training, 10,000 validation, 10,000 test. So there will be 3 sets of data there. But that point's not that important right now. But when you see 50,000 come up, don't be surprised. Okay. How would we go about analyzing these images? They're 28 by 28 pixels. First thing we're going to do is just do the dumbest thing we know how to do, and that is linearize it. 28 times 28 turns out to be 784. So we're going to have 784 input parameters to our network now, 1 per pixel. Okay? Each entry will consist of the grayscale value, 0 to 1, for that particular pixel. The output is going to consist of one hot encoding of the output. Who's done one hot encoding before? Okay, there's nothing to it. It's exactly what we were just talking about. It means 7 is represented by this. Okay, a vector 0, 0, 0, 0, 0. Oh, it's a 7, 8, 9. Okay, I've got a 10-dimensional or 10-entry vector. One of them is a 1. The rest are zeros. That's called one hot encoding. I don't know where these names come from. I really don't. Okay, so we're going to have 10 output nodes for our network, 784 input nodes, and we're going to use one hidden layer. Because we have one hidden layer, we can use the code we just used, second network. Okay? Who's with me? We're okay? All right, let's do it. There's code that you download. It's called mnist loader. Import it. Okay, import mnist loader. And then get the data. The function's called load mnist 1D. There are a lot of outputs. I apologize. Train in, train out, val in, val out, test in, test out. But that's the way it's been set up. Take a minute and write it out. What's that? Where are you?
I know I'm on sign it.
Some keep dims equals true. Which version of Python are you using?
I'm on sign it, so we
2.72. The default, did you load a module? Which one? No, go to a higher one. Go to 278. Once you've loaded your data, shrink it down. Because the data at 50,000 points is too big for what we're going to be doing. Unless you want to start it and come back after lunch. It might be done by then. Just take the first 500 entries. Okay, that's what these two lines are doing. And then run your network. Same code as before, except we'll have 30 nodes this time instead of 10. Train in, train out. The output dimension is 10 now instead of 2. Eta of 4e to the minus 5. And do 20,000 steps. This is going to take a few minutes, so don't be alarmed. Though your computer may be faster than mine, so mnist loader. Okay, train in, train out. As it happens, I've done this before. Get my data, train in to get the first 500 points. Okay, train out to, good, and model 30 nodes, just those 500 points because as you'll see it's, well, we'll come back to that. Output 2, output dim is 10, eta is 4e minus 5, and num steps is 20,000. Now, the number of parameters has gone up by more than 2 orders of magnitude. So it's a little slower than it used to be. Is it working? Problems? It's okay. 84, let's see. When I got this, I did 98.8. That's not bad. Let's see how I do this time. 89, we're getting there. We're only at 4,000 steps. We're getting there. What's your top number? 100! Ah, we have a winner. Yes, sir.
I was just going to ask you, because it's sometimes hard to keep track of what those vectors mean. So do you think And I imagine it just should be your input data.
That's the input data. So that's 50,000 by 10. Sorry. 50,000 by 784. Excuse me. 10's not right. That's the output dimension.
I see. So the output is just like the corresponding factor, like 0, 1, 0, 0, etc.
Yes, exactly. So you got 10 output neurons, each one hot encoded. You take, again, the maximum value, which is the index of the one you want, either 0 through 9. Okay? 30 is the number of nodes, so we upped it to 30 this time. Is that any better?
Trying to code again. So
Oh, okay. 98.4. Ah, awesome. 100%. How does it look on the test data? Uh-oh. We'll come back to that. I'm only at 14. Oh, 99! Oh, I'm totally going to win. All right. Test data. If you're done, go to the test data. Here's the test data slide. I only grabbed the first 100 just because, again, you don't need a huge number for this. 82 on the slide. Let me see how I did them when I actually did it. Or just now. Let's see, 99.2. Getting better. You got 100% though. I'm curious. How Don't expect to get 100% necessarily. You may actually if you run it long enough. It's a function of the randomization of the variables at the initial stage. So sometimes you'll do better than other times. 99.6. All right. 99.8. Oh, I'm awesome. All right. Let's do it. Test in 2 is just the first 100, not int. Oh yeah, in. Okay. Test out 2 is the first 100. F is sn.predict. Test in 2. Okay. All right. Sum of F tests. No, that's not right. Get out of there. I don't want that. Sum of F is equal to test out 2 divided by float length test. You know what? It's 100. 75. Oh dear. 75. How'd you do? 70. Ah, I beat him. All right. As you can see, here's the numbers, right? 784 weights plus 1 times 30 nodes plus the output layer of 10 weights plus 1. Oh, that should be a 30. I'm sorry, that's wrong. So there's 23,500 in the wrong answer. It should be higher than that. That should be a 30 plus 1, right? 30 weights on the output node plus 1 for the bias times 2. Man, I'm off. Times 10 for the output nodes. What is that number? I'm curious. Let's do it right. 785 times 30.
784.
Right, plus the bias. Right? Plus the bias. So that's right, plus 31 times 10. 23,860. 23,860 free parameters for a 500 data point fit. We're in good shape, team. You can see the problem, right? So this is a prime example of good intentions not working out very well. Okay, we have some overfitting going on in a big way. How are we going to deal with that? Let's talk about overfitting strategies. Everyone with me? We're okay to move on? All right, well, okay. As you probably know, overfitting happens when you've got so many free parameters that you can fit every single detail of the noise in your data instead of just focusing on the grand themes of the data so that your model will generalize to data that is not in your training sample, right? If we excessively fit to the noise and get 100% accuracy on the training data, the odds of us getting 100% on the testing data are pretty low. Okay? How do we deal with this? The first thing you can do, more data. Always recommended. Get more data. If you can, throw more data at it. Real or imaginary. What do I mean by that? The example, a very good paper on this particular problem was done by a group that took the MNIST data set and took every image and moved it by 5 pixels and then rotated it by 2 degrees in random directions. And suddenly, instead of having 50,000 data points, they had 250,000 data points. And they got fantastic results on their test data. If you can do that with your data, create artificial data, do it. Absolutely, it will help your models. We'll do the full 50,000 data set later, after lunch, because we can't do it with this algorithm because it'll be too slow, but I'll show you how to do it after lunch. But if you can get more data or create fake data, you do it. Okay? And if that just means taking your images, if you're doing image analysis and just tweaking them slightly, it's perfectly good newish data, new enough data. Okay? Regularization and dropout. Who knows what regularization is? Some of you have used it. Okay. It shows up in all sorts of mathematical problems where the problem is ill-posed. And then dropout is a uniquely neural network approach to fixing overfitting. Let's talk about regularization. Adding data is obvious. You guys understand what that means. Regularization. Regularization is an ad hoc technique by which we're going to punish weights that get too big. Okay, we're trying to prevent individual pieces of the model from becoming too important to the model. Okay, it shows up all the time, especially if you're doing any sort of inverse problems. Inverse problems, good. Seriously, they're hard. They're really, really hard. Inverse problems are the sort of problem where, like radar, I shoot a beam and I get this data back, and the data has integrated everything it hit along the way. And I have to back out what was there based on not enough information. Or I use sound waves and I'm penetrating the earth looking for minerals, or any sort of problem like that, where the signal you get back has integrated everything along the way, and there's not enough information to back it out. These are called ill-posed problems. Regularization is used all the time. Tikhonov regularization is a name for it. Ridge regression is another one. Okay, it usually shows up like this. There are other forms, but this is a very common one. Here's our regular cost function, right? You've seen this before. This is our output from the network. This is our data, right? So that's our quadratic cost. And now we're just going to add this term on the end here. Take the weights, square them. Here's a parameter. It's called the regularization parameter, meaning how hard are we going to crush these guys? And there's a factor of 2 because it's squared. Okay? If the W's get too big, the cost function goes up and things get unhappy. All right? We're trying to minimize the cost function. That's what gradient descent does. If these get too big and lambda's big enough, the cost function is going to start to rise, and the gradient descent is going to say, no, I don't want to do this anymore. I want to go back down my valley of parametery goodness, whatever you want to call it. Okay? Lambda is the regularization parameter. Sum of j, in this case, is over just the weights. You can do biases too if you want to. Weights is sufficient generally. Okay? Is everyone with me? Is that good? Same thing shows up when you do inverse problems in the exact same way. If C naught was our original cost function, so this is our new cost function, the original cost function plus this new term, W squared, Okay, this is going to change how our gradient descent works now, right? We have to change our derivatives. So our new derivatives for the weights are the original derivatives for the weights plus this new term, lambda WK. All right? So our new update for the weights looks like this. In particular, this last line. WK is now 1 minus eta lambda WK minus eta, the old term. Okay, good. We saw this already. Actually, I told you to ignore it, but it was right here. We saw this code already. This is second network, right? Second slide of second network. This is the update of the parameter stage. Lam was that lambda term. Okay, we set it to 0 before. By default, it's 0. Okay, but if we wanted to add regularization to the code, this is where it would show up in the weights, right? Lambda times eta times the old W1 plus the original derivative that we worked on through, that we got through the backpropagation algorithm, right? Okay, same with W2. Again, you could put it in the B's if you wanted to. It's generally not done, but you could. Usually the intercept is less important. It's less tied to the data, if you will. Good? Okay, run it again. Lambda equals 5. Same thing, exact same code. 30, train in 2, train out 2, output dimensions 10. Eta is still 4e to the minus 5. Just up arrow. Where is it now? Okay, there it is. Okay. Lambda equals 5. Again. How are we doing on time here? Okay, that's not too bad. It's not too bad. 2080. You won't get 100% this time. It's okay. I'm not going to hold it against you. Because again, the role of the regularization is that it's going to try to keep the model from focusing too much on any detail in the data and go for the broad themes in the data, general trends, and it allows us to improve our testing, our performance on the test data. Takes a while though. Come on. 91.2. So in this on this slide, I only got 93%, but my performance on the test data went up to 87, which is significantly better than it was before. What was it before? I don't even remember now. 75. Well, that's what I got this last time. I'm curious what the slides were. So on the slide, I got 82 the first time. Again, your numbers will vary. 98.8. This time I got 87, so that's better compared to 82, though the actual training data doesn't do as well. And this one will go up to 95, 96-ish maybe. Anyone finished? 100. No 100. 96? All right, and on the test data? You got 96 on the test data. Oh, do the test data. You got 96 on the training. Okay, do the test now. 83. Much better than 70. Okay. Good. Am I there yet? Okay, anyway. Anyone else done? How'd it go? Better? Better. Tell me it's better. Please. Okay. 1205, 17,000. Oh, we're so close. Yeah, 96. And 96. And 96. And here we go. And the winner is 96.6. Okay, F is to some, and this time I got 85. Improvement. Better than 75. Okay. Okay. Again, regularization is keeping any particular weight from getting too important. Okay. It allows it to more generally fit to the big picture, if you will. Okay. Trial and error, again, is what you need to do to find lambda. Okay. There are some guidelines out there you can find depending on the size of the data and stuff and the number of parameters, but again, that's how I found it, just by trial and error. I haven't found regularization to be used in neural network training as much as it used to be. Dropout seems to be gaining in favor. It's a relatively new approach, but is quite popular. So we're going to talk about that. Any questions about regularization? Okay, dropout. So dropout is weird. So as I said, it's a uniquely neural network way to prevent overfitting. And what it does is it just randomly drops neurons from your network. And then puts them back and drops out another random set of neurons. And then another random set and another random set. And you just keep training your network on a slightly different network every time. So what ends up happening is you end up sort of like averaging over a whole bunch of different networks instead of one network. And consequently, what seems to happen, and I use that term intentionally because people are still trying to figure these things out, what seems to happen is, again, the network learns to not depend on any particular parameter too much because sometimes it's not there. It's just gone. It drops out. Okay? Different fractions of the layers can be specified for dropout. Trial and error, again, is helpful here. Minimum seems to be about 20% of whatever network you're working with. Up to 40, even 50% of your network can drop out for any given iteration of the gradient descent. The paper that wrote it found that 20% seemed to be the minimum to actually start making a difference. Above 50%, you're just dropping out too much. There's no network left. You start to run into problems. Okay? So you will find this quite commonly when you start looking at schematics of networks, when you start reading papers in the field. People lay out their networks so you can see what they look like, though you'll see dropouts in spots. Okay? And dropouts, this is what they are. Obviously, the output from the layers has to be scaled. You have to be, well, you can see the problem, right? If I'm training the network, and I'm dropping out 20% of my nodes every time, and then I'm done training and I put all the nodes back, suddenly the output's going to be too big because there are too many inputs to the final layer. Actually, I'll show you rather than describe it. So imagine this was our first network. This is what dropout would look like. We're not going to do it because I didn't feel like trying to code it up, but this is what it would look like. Okay? Our hidden layer is randomly losing nodes with each iteration of gradient descent. Okay, so the first iteration, the second node, and the fifth node disappeared. This one, a different pair disappeared. And this one, a different pair disappeared. You'll notice that it kind of complicates things when you put things back together. That's where the scaling comes in. Okay, you have to sort of average over the inputs. Exactly. The output nodes still have 6 inputs, right? But in every particular case, only 4 of them are being used. So you have to do some scaling when you put it all back together. So when you use all 6 inputs. Otherwise, essentially what's happening is those other 2 inputs are treated as 0 for this during the training. One other thing you may see, I've never tried it myself, but I've heard that people will do dropout on their input, on the input layer, meaning they just start dropping out input from their data. So instead of, if I've got 784 inputs, I'm only going to use 700 of them or something at any given iteration of my training. You can do it on that layer as well. Does that make sense? It's kind of weird, but it works for the same reason. For a different reason. It's like averaging networks. So it washes out any particular bumps and valleys in the parameters. Yes, sir.
I have a generic. Size of the parameter space, number of parameters, essentially the size of your network. As you're saying, you can overfit depending on what you're doing. Are there guidelines? Are there heuristics, or is it just you learn by experience kind of?
You learn by experience kind of thing. What's that? The question is, how do you figure out what you're doing? How do you construct a network is an open problem. There are competitions for, here's my data set, come up with a network that fits it as good as well as possible. MNIST is outdated now. It used to be based on MNIST. Now there are data sets where you've got images in them with 1,000 different types of things that could be in there. Bicycles and birds and people and rocks and whatever, trucks. And you have to classify that image based on what it is. You've got 1,000 outputs, hundreds of thousands of images. And these competitions, they publish the results, the winners. So you can use these as starting points. There are sort of classic networks. Someone will say AlexNet or GoogleNet or KLNet. And these are sort of become sort of historical benchmarks in the development of the field. And so you can say, okay, this network had so many layers of certain types, and there was a dropout and this, that, and the other thing. It's a lot of trial and error. It's a lot of reading the literature and talking to your colleagues, really, is the short answer. Other questions? Sorry, it's not a very good answer, but it is the way it is, I believe. Yes, sir?
Follow up on that. The pool grading algorithm optimizes the number of.
Absolutely. We'll talk about that, but we won't be doing that. Are there algorithms out there that optimize the number of nodes and layers? And those are, can't remember what they're called. They're on like the third last slide in the other things you need to know about slide. We'll come back to that. But the answer is yes, those are out there, and this is a very active area of research, obviously. Other questions? Okay, I think that's a good spot for lunch. Let me check here. Yes, we're moving on to now frameworks. Okay, so let's call it lunch, and we'll come back at 1:15. We'll stay here. If you want to leave your computers, we're going to eat in here. So if you want to just leave your stuff, it will be safe. You know what? We'll